All right, so my video cut off in the middle of this problem, so let's keep going. All right, so this problem is looking for what mass of radium-226 is needed to give an activity of 2200 becquerel. We don't have an equation that has mass in it explicitly, but we do have an equation relating activity to the decay constant and the number of undecayed nuclei. So one of the things that we know as kind of an aside is we can relate the number of particles to a mass, right? We know that 1 mole is equal to 6.02 times 10 to the 23rd particles. Oops, CLES. Okay. And then for radium-226, that means 1 mole is equal to 226 grams. All right, so if we know in this problem, if we're able to plug in 2200 becquerel equals 1.35 times 10 to the negative 11 inverse seconds, and we get n, right? We would solve for n, and we would get that that is equal to 1.6 times 10 to the 14 undecayed particles or nuclei. Okay. And we can do a little unit analysis here where 1 mole is equal to 6.02 times 10 to the 23rd particles. And we know that there are 226 grams per mole. And so we can cancel out the moles and cancel out the particles. And we end up with a mass that's equal to 6.12 times 10 to the negative 11 kilograms. Okay, so doing a little chemistry with our physics, kind of in a little unit analysis, we're able to use our activity equation to come up with the mass that's equivalent to the number of undecayed nuclei. All right, so how can we predict which particles are most likely to undergo some sort of nuclear decay? Well, it really depends on their location, or what their nucleus is made up with, and their location on this graph. So on the graph, we've got on the y-axis the number of neutrons in a nucleus, and on the x-axis we've got the number of protons. Okay, and we can use this to predict the stability of a particular nucleus. All right, so this line here is where the number of neutrons is equal to the number of protons. These dots here are generally, this line is called the zone of stability. Right, so the most stable nuclei are along kind of this dotted line here. Above the zone of stability are generally neutron-rich nuclei, right? They have more neutrons than protons if they exist in this region up here, right? And so that means if they decay, they will undergo their beta minus emitters. And they'll undergo beta decay, beta minus. And what that means is if they're neutron rich in beta decay, like we've talked about, right, we've got a parent nucleus decays into a daughter nucleus, right, plus a beta particle and an electron antineutrino. But what's really going on in that nucleus is that a neutron is turning into a proton plus an electron, right, a beta minus, plus an electron antineutrino. Okay. So if you're neutron rich, the way that you can become more stable is for a neutron to turn into a proton, right? That will make your nuclide more stable. And in that process, you also emit a beta, negative beta, and an electron antineutrino. If you're down in this bottom right-hand corner, that means you've got more protons than neutrons, so you're considered proton rich. Okay, and this is a beta positive emitter. And this, or something called electron capture. And we'll talk about that a little bit more as we get into particle physics. But to become stable, if you've got more protons than neutrons, right, to become stable, you want to get close to an equal number of protons and neutrons. So we had with beta plus decay, right, you had a parent nucleus turns into a daughter nucleus plus a positive beta and an electron neutrino. What's really happening is a proton is turning into a neutron plus a positron, or a beta plus an electron neutrino. Okay. So a proton is turning into these things. All right, so they're physically changing from one thing to another in an effort to become a more stable nucleus. All right, so properties of a stable nucleus. For smaller nuclides, 1-to-1 proton to neutron ratio. So what that's looking like, right, smaller nuclei down here, a 1-to-1 ratio will make you stable. Even, not odd numbers of protons and neutrons tend to be a pattern for stability. And then number of protons, number of neutrons, are both equal to one of these magic numbers. And they're magic because there's not really a pattern. We just notice that these numbers, atoms with these numbers of protons and or neutrons, tend to be the most stable. All right, and then finally, if we go up here, up kind of above this region at a certain point, higher numbers of protons and neutrons, those tend to be alpha emitters. I'll just write that in gold for funsies. Okay, so why do these decays happen? Well, the mass of a decaying nucleus was greater than the combined masses of its products. There's an energy that is released. The binding energy, the amount of energy binding a nucleus together, is less than the energy binding the products together. And then as a pattern, elements to the right of nickel on a element curve are not bound as tightly. So let's take a look at that curve. Okay, so what we're seeing here is the amount of energy that binds a nucleus together. Okay, it's called binding energy, right? And not only do atoms or nuclei want to be stable, but we do see that there's a certain amount of energy that's required to hold a nucleus together, right? And as a result, there's a certain amount of energy that's required to rip it apart. And that's called binding energy, and it follows kind of this curve, right? So there's generally less binding energy with lower atomic mass numbers, and then we get up to nickel up here, like nickel iron-ish. That has the highest binding energy, which indicates that it's one of the more stable nuclei. And then that binding energy generally decreases after nickel as we increase in atomic mass number. Okay, so what does that tell us? Well, it kind of is able to indicate not just when a nucleus will randomly decay, but it can tell us which atoms can be torn apart and which atoms can be fused together. All right, so this is a very similar figure. Here on this one, they're using iron as kind of that flux point for stability. Again, iron, nickel, and I are right around that turning point right there. So sometimes you can see an atom not just undergo beta or alpha decay or gamma decay, but you can rip a nucleus apart or take two and put them together, right? So fission is taking a nucleus apart and in the process releasing energy. Fusion is putting two smaller nuclei together and in the process releasing energy. And again, binding energy is the energy required to hold a nucleus together, and it's how much is released when you tear it apart. Okay, and typically I would, in some other years, I would spend some time doing a simulation looking at this, fission versus fusion, but we're just going to plow through for this year. All right, so again, fission versus fusion. Fission is when a heavy nucleus splits up, energy is released because the produced nuclei have higher binding energy than the original nucleus. And then fusion is when two lighter nuclei fuse or join together, and energy is produced because the products have higher binding energy. Okay, so there's always a difference in the amount of energy between the parent nucleus or nuclei and the daughter nucleus or nuclei, and that difference is what is released. Okay, so for a light nucleus to fuse, very high temperatures are required. They're positively charged. Nuclei are positively charged, so electromagnetic repulsion will force them apart unless they become so close together that the strong nuclear force can take hold, right? So what that means is we need to increase the temperature of a particle if we want fusion to happen, so that nuclei can have enough kinetic energy that they can get close enough together. Then fusion can occur.